right. So let's jump right in, everybody. Let's see. Let me just get everything set up so I can see your comments. Feel free to ask questions in the chat. And I'll monitor the chat for questions as I go through. So so that was a wonderful introduction. I probably don't need to cover this stuff, but yeah, I've been working in this area for quite some time, right? So I've seen the pre-generative AI era of AI, and also have been with fervor innovating in the post-generative AI era. And it's been quite a journey. So this is a picture of what AI thinks when it thinks of itself consuming the world. This picture was generated by essentially a neural network. And it really goes to show how much progress we've made. But many folks might be wondering, we've always dreamt about artificial intelligence. We've always thought of this as something that we wanted to have technology represent. We see it in the movies from the 1960s onward, from Star Trek to Space Odyssey 2001. We've been contemplating AI. It's almost, when you look at the trajectory of computing and the trajectory of computing technology, from the advent of the computers, which happened around the late 70s, early 80s. Oh, hello? Was that a question?
No, I think Professor.
Yeah, cool. Yeah, I mean, computers started big. They were huge, right? They were mainframe computers. And we've only made them more powerful, more smaller. And we went to PCs, we went to smartphones, ultimately, we went to laptops, we went to smartphones and tablets. We're making computing more personal, fundamentally, right? And so that are the early archaic steps toward really creating an external intelligence, which we've gotten to essentially achieve at this moment. So when you look at the trinity of advancements required to create this era that we're in, it really comes from having not just the models, the neural network models. Those models, the models we're using today are essentially versions of inventions that happened in the 60s, 70s, 80s, right? We've done a couple interesting tweaks to the models. We've created the attention mechanism, which is just a different kind of neural organization of neurons and weights and neurons. But really what has gotten us here is the simultaneous advancement in processing, the simultaneous advancement in data, and these things come together to allow us to have entered this era. Now, we had an early entry into this era with Siri, with the first manifestations of AI from a consumer perspective, right? And so we had Siri. There was a project called ImageNet where we did the first really interesting image classification using neural networks. And this was the early days, right? I call this the Palm Pilot days to what will ultimately be the smartphone. So a lot of folks in the room probably don't know what a Palm Pilot is. Perhaps more people know what a BlackBerry is. But when we had Siri and Alexa, the very simple conversational experiences, we had very simple image classification. We were kind of in the preamble of what would be our iPhone moment. And I describe this as the iPhone moment because at this stage, if I talk to my mother, who's 77, some of her first questions are, so tell me about this AI, what's going on, right? If I talk to my kid who's 8 years old, he's playing with AI online. Is that what you work on, Dad? Like AI is the thing. So that's the iPhone moment, like my mom didn't know what a Palm Pilot was. My kid wouldn't have known what a Palm Pilot is, but everyone knows what an iPhone is. Well, it's the same with AI as of 12 years later, right? So the first entries, early tech, not many folks are really using it in their lives. Now everyone knows about and desires and wants this technology. And that was with what happened with ChatGPT. Now, this was a very, very important moment, right? Because both the tech industry, the small companies, after this moment, November 30th, 2022, the smaller companies, the tech industry, were hyper-focused on this. The venture capital market was hyper-focused on this. At the same time, the largest companies were hyper-focused on this. So, you know, in the first 6 months after ChatGPT launched, there was a surge in deal flow in the VC market, in the startup community, funding AI technologies. Indeed, there are a number of VCs, there's a number of investment theses where they'll only invest in AI technology. It's consensus that technology as we know it is going to be innovated through the lens of artificial intelligence. That has been accepted by the startup community, by the investors in the startup community. These are the top investors in the market. And keenly focused. I mean, a lot of these companies you guys may not have heard of, but these are actually the movers and shakers. I mean, I'll point a few out. 11 Labs, they're really at the forefront of creating voices that sound like you. So you can have a virtual assistant that sounds exactly like you. You know, Adept is doing some innovative multimodal model work, right? So where you may want a model that can understand what it sees, so it looks at pixels at the same time as looking at text. Adept is doing some interesting things there. You might notice Anthropic. I mean, everyone knows OpenAI, but not a lot of folks talk about these companies as much. My mom doesn't know who Anthropic is. My kid doesn't know who Anthropic is, but Anthropic just garnered a, $2.7 billion deal from Amazon. You guys might famously remember the what was it? $10 billion deal from Microsoft to essentially get the the rights to monetize OpenAI. And you know, like Anthropic is doing the same. I mean, it's a lower price, 2.7 billion, still in the B's, but that's Amazon's play. And actually, what that represents is it's not a small company thing only. This thesis that AI is the lens of how we innovate, it's through AI is how all innovation and technology will be keenly focused on, right? And when I say all, I really mean the vast bulk of the innovation will be keenly focused on AI. That's also a view that's shared by the top companies in the market. I just clipped this from today. Every time I need to show this slide, I have to clip a fresh one because it's changing like crazy. NVIDIA is number 3 now, which is bonkers, right? Why is NVIDIA number 3? Oh, because AI needs GPUs. So everyone's buying these things, right? So, but when you look down this list, right, a couple things you notice. Number 1, it's mostly tech companies. Actually, out of these 11, I think 9 are tech companies. And you know, Berkshire Hathaway essentially invested in the other 8. That's why they're on this list. That's an investment group. That's Warren Buffett's company. But we see Meta, we see Alphabet, we see NVIDIA, Apple, Microsoft. Microsoft did the $10 billion deal. Amazon did the $2.7 billion deal to get Anthropic, right? Anthropic did Claude 3. So some folks who are dabbling in AI might be aware of Claude 3 as a very innovative model that's giving GPT-4 it's challenging. It's the challenger model to GPT-4 and is doing some impressive things. But all of these folks are placing their biggest bets on AI, right? Apple actually has a project in the works. I don't know if you guys have heard of it. Of course, Google has been scrambling to take back the throne when it comes to AI innovation. Indeed, the transformer neural network, the model that is fueling this stuff, was actually invented at Google and really kind of pioneered by Google, the transformer neural network. So small companies, all in on AI. Big companies are also all in on AI. So that begs the question, and this is very important, right? So for this audience, I do want to spend some time talking about what is this technology fundamentally? And then we're going to talk about where innovation is likely to come moving forward and where the focus of innovation has been since the moment, that epoch that the whole world has recognized that AI is the landscape of future innovation, right? Like what is actually happening? And so we'll talk about that after we look at what this technology really is. So first, we need to lay out the space a bit. Like, what is generative AI is really the key tech that everyone's focused on understanding how to wield it to solve problems and how to advance it to solve bigger problems. But AI is a broad term, right? It really covers any kind of computer or machine mimicking intelligence, right? So you could actually have a number of if statements in a loop. And if it's mimicking intelligence, human-like intelligence, it's classified as AI. Now, machine learning is the class of AI that learns from data. So it detects patterns in data sets and then can make inferences based on those patterns, can make predictions based on those patterns, right? And a regression model is machine learning AI. A decision tree are other types of approaches to machine learning AI. Now, a particular class of machine learning AI, these are the AIs that learn from data, are deep learning models, right? DNNs, deep neural networks. These are the class of such models that learn from data that mimic the neurons in the human head, in the neurons in not just humans, many animals' brains, right? So if you're simulating neurons on the journey, it's deep learning. And there's a more nuanced definition. A deep neural network has more than 2 layers. It has hidden layers. And then you have an artificial neural network, which is just two layers, essentially. There's no hidden layers. But all of that is deep learning, okay? Now, Gen AI is a particular class, a particular approach to how the model is formulated, right? So it's a certain set of these neural network-based models represent your deep learning models. And this is really an intuitive way for us to proceed, right? So there's an experiment I often talk about where there was an attempt to experiment whether neurons can learn new information it wasn't designed to ever be exposed to. And so in this experiment, they put pigeons in the Skinner box, and they would try to train the pigeon to tell the difference between 2 artists just by looking at the work. So Van Gogh and Chagall. And they got insane results, right? This was a very important piece of work, piece of research in neuroscience, that neurons can learn information that brain was never really designed to be able to learn. So neurons learn, right? And it's this is now a trivial it's trivial statement, but the computer science, the scientific community took inspiration from biology. This is the advent of the neural network, right? Now that we understand how neurons work to some degree biologically with electrical pulses and the likeliness of pulsing based upon the input pulses through the dendrites from connected neurons. So you can model that mathematically. So a neural network is really a mathematical model for which you have a node, which represents the neuron, and then there's inputs, which represents the synaptic connections between neurons. And then there is a calculation as to, based upon how strong those input signals are, you could think of these signals as values between 0 and 1, based upon how strong those input signals are, how likely should I be to propagate that signal? and at what level, right? So you can learn that with coefficients, with what we call weights. Weights are the coefficients that are proportional to the input signals coming. These are values, and often between 0 and 1, that propagate through the neuron. So I have a question here, or a comment. Yes, so we have a comment, sir. If I conclude the connection between AI, ML, and deep learning, is it like this? We create an NN under deep learning, and we need to train it. So we will be using ML models to train them, or finally, we deploy it. Users don't see the procedure, so we call it AI. Is that it? No. So the point was really to describe the landscape of technologies that are called AI, and to understand that AI is a broad class of different approaches to achieve it. There's different techniques to achieve AI. And so we're actually only really excited and in the realm of one such technique, which is the generative approach. And so we're going to talk about the origin story of generative AI. And the origin story starts with the inspiration of the neuron, and then some happy accidents and discoveries that happened on the journey of innovation. So that's what a neuron is, right? And so what we were able to show is when you put enough of these things together, you can have it solve some interesting problems, right? So digit recognition is a very interesting problem. This is a very basic neural network. It's exactly what I showed before on this slide: inputs, node, output, with an activation that will take those inputs and then propagate a signal through. And you can build a machine, essentially, out of these neurons that will look at 784 pixels and make a prediction as to what is the digit between 0 and 1 represented in those 784 pixels. You can imagine taking this picture of the 5, taking each individual pixel of that 5 and putting it onto a one-dimensional line, right? Just taking all the rows and then laying them out into a one-dimensional input layer. And then those pixels are values between 0 and 1, 0 being black, 1 being perfectly white. And then all the grays would be your 0.5s and 0.7s and 0.2s. And you can put these pixels through this neural network, and the neural network will tell you what digit is in that picture, right? And so this is called MNIST. This is a very important model. It's used as a canonical model for demonstrating the efficacy of neural networks. And this is a model that actually beat human accuracy. Like, this machine does better than humans at recognizing digits that are handwritten, which is kind of crazy. So this was one of the first real interesting story points, right? Neurons are interesting. When we simulate them in a computer, we can actually get this neural network to do better than humans. So neural networks are interesting, right? So that was the first kind of major step that I would say is an interesting milestone for AI. Now, we're going to teleport, and that's very old work. We're going to teleport to circa 2012, right? Which is like 10 odd years ago, which is crazy, to 12 years ago, whatever. So this is a different drawing, but it's a very similar neural network architecture. It's called a feed-forward neural network, right? And if let's just look at CBOW, okay? Continuous bag of words. So this CBOW model, what it does, this model is designed not to predict numbers between 0 and 9. It's designed to predict the missing word, right? So if you have a context window of, say, one word on the left and one word on the right, this shows a context window of n words, right? So, or k words, essentially. But you can imagine just 2. So it looks at 2 words, the left and the right, and it predicts the missing word that should be in the middle. So The interesting thing about this neural network is you can let it learn to make these predictions by giving it unstructured text. That means you don't have to label the text. You can let this model read text to learn to make this missing word in the middle prediction. So this is a very powerful step because it produced an innovation that created an accidental insight that put us on rails to end up where we are today with ChatGPT. This was really I would argue that this moment was the start of the unstoppable journey toward ChatGPT in 2012. Why is that, right? So the cool thing about this model is it's called self-supervised. It means you don't have to label the data. With the pictures, you actually had to have a training set where humans were like, that's a 1, that's a 5, that's a 7. And then it would use that training set of labeled data to learn how to predict numbers when it sees. So it's like the examples used to teach a child algebra, right? So you teach the child algebra with existing problems for which they can check their answer. That's the training set. And then once the kid learns algebra, then they can solve new problems they haven't seen before because they understand how to solve it by checking their answer to learn, right? That's a training set. Now here, the training set is the text itself. So you can give this model Wikipedia and it'll look at every sequence of, say, 3 words, like in this example, and then learn to predict the missing word. It's intrinsically labeled, you can think of it. So that's important. That's important. It means if you have a lot of such data, these models can learn, have a lot of data to use to learn without humans training it. That's one nice, important feature of this model. The other reason that this started this unstoppable train was because there was a happy accident. They discovered that this model will learn more fundamental, conceptual, and abstract relationships about the word by just learning to do that prediction. You could leverage this model once trained, once it reads Wikipedia, it learns more, it learns to do more than the task you gave it. It learns to do more than predict the missing word. That was in the other one. And that one was an accident. And I think I have this slide next. But what does that mean? What does that mean? It turns out that that hidden layer of this model will allow you to create, you can use the numbers, the weights that were learned to create something called an embedding. Fancy way to say a multidimensional point in space, right? It's a vector. So you can create a vector representation of words. And the nice thing about vectors is you can do math with vectors, right? You can think about a 3-dimensional point in space, a Cartesian coordinate, right? Reduced to a vector, but n-dimensional. Beyond that, let's say you have 5 12-dimensional points in space. Well, you can add, subtract, divide, and do interesting things with points. And what was discovered is after we had those embedded representations of words, we could do crazy math. The model must have learned something meaningful by reading Wikipedia, which is if you subtract the vector for king, you subtract the vector for man from the vector for king, and then you add the vector for woman, the model would give you a vector for queen, right? Or another way to put it is a vector, is a point, is an embedding that its closest word embedding would be queen, right? To just be a little bit more precise. But so this was interesting. It's like, oh my goodness. So like somehow this model just read Wikipedia, and in the information in that latent space, in the information in the vector space, there is an encoding of information that captures the notion of gender. The notion that if you remove the man from a king concept and you add the woman concept, that is a queen. That is captured in the model's brain. It's represented in the information captured in that latent space, in that vector space, in those vector embedded representations. That was a happy accident. How do we know? because the paper that discovered it says so. And this is one of the most important things about AI research that a lot of folks don't fully understand, that should really try to strive to understand. The important thing that's kind of a shocker is much of the innovation that's happening is not necessarily deliberate, intentional, or forecasted by the folks doing that innovation. So the paper itself that has this discovery says, somewhat surprisingly, it was found that similarity of word representation goes beyond simple syntactic regularities using word offset techniques where simple algebraic operations are performed on the word vectors. It was shown, for example, that vector of king minus vector for man plus vector for woman results in a vector that is closest to the vector representation to the word queen. Wild. Somewhat surprisingly, that little surprise is what inspired the next generation of research. So I'm skipping a couple interesting steps because then we had glove embeddings, then we had Elmo embeddings. There's something called an LSTM that was really interesting for a while, but then got really uninteresting because training it is slow. But that takes us from 2012 to 2015, 2016, 2017, whenever, to the invention of the transformer. And the transformer, invented by folks at Google, the intention mechanism, that is what that's the revelation that got us to today, and I'll tell you how. But that was created by Google, and very good work. And what it does is it essentially is a model designed to do that thing where it learns about the world from reading text, right? That's one of the applications of this model, is this unsupervised approach. Of course, you could do language translation, all kinds of stuff with it, but it's a similar thing, this kind of self-supervised, pre-trained, zero, a model reads and then learns about the world, and then you can use that to solve various problems. This was actually invented because LSTMs are too slow, but that's a story point for another time. Anyway, so Google invented that. And what it really is the picture on the right, right? The picture on the right is the transformer, and there's various ways you can use a transformer. So you can break it up, you can use the encoder part, and I won't get into too much details on this, but you can use the encoder part to create interesting embeddings. That means of like a sentence. That means you can take a sentence and you can create those points in vector space. And those points capture conceptual, semantic richness of what the sentence means. And so that's like an encoder kind of way of using the model, right? To create rich embeddings. So you can do things like that algebra, but do even more things, because in the information space represented by that vector space, there's rich information organized in that space, right? It's another way to think about it is it's like when you think of the word apple in your brain, taking a snapshot of all your neurons. That's an embedding, right? So the model will read the sentence, and then as it's understanding the sentence, there's like a snapshot of all the neurons, and then you print that to a vector number, and that's an embedding, right? So that's an encoder, like, realization of it. Another realization of it is you can train that transformer and just use the decoder. That means the decoder is the part of the model that takes that snapshot of thinking and then can write, right? But you just take the piece that can write and you just give it a preamble of a sentence and then let it write the rest of the sentence. That's the GPT, the generative pre-trained transformer. It's the part of the model that writes. So you can think of the encoder as the part of the model that reads, and the decoder is the part of the model that writes. And so that decoder is all the stuff we're using today. Of course, when you train it, you use the whole thing. You train it on both thinking and writing, but actually, well, there's a piece of work, it's called T5, that demonstrated that using the full encoder and decoder of the transformer actually yields the best results, though the GPTs that we know and love is not that work. That T5 work came from Google too. indeed, from the model perspective, Google has been on the forefront from the model perspective, and even the stuff we're using today doesn't represent the best possible model, perhaps. But you know how things go. I mean, the Apple computer may not be the best possible computer, or like the iPhone's a better example. Maybe the iPhone isn't the best possible computer, but it's the most popular, and it's what people are going to use, right? Like, I'm sure there are Androids out there that are better than the Apple computer. I mean, the Apple iPhone, but that's how markets work. Anyway, so that's really what's going on in that pre-trained transformer. So things got fancier, the models got smarter, and then there was a big innovation. This is where OpenAI. So OpenAI really popularized the decoder-only approach. It was a battle, though. There was a number of folks doing interesting work in that space, but the decoder-only approach was really kind of pioneered by OpenAI, basically taking the decoder, making it really large, and then training it on more and more data, trillions of words from the internet, et cetera, is what was demonstrated. And then that was actually kind of a stealth mode mind blower. There's something called zero-shot learning, few-shot learning, like this stuff. This is actually what we're doing today. Prompt engineering is essentially zero-shot and few-shot learning. If you're solving problems with prompt engineering, you're doing zero-shot and few-shot learning, but nobody's really calling it that anymore because prompt engineering is sketchier, I guess. So let's go. But that's really what it is. Anyway, there was a community, kind of like the Palm Pilot community, that knew this and was like, oh my goodness, this is going to change the world. So Microsoft very, very savvily paid $1 billion to get this tech. And last time I mentioned this, oh yeah, at this point, Microsoft spent $1 billion on this tech, and then someone was like, no, wasn't it 10 billion? Like, what are you talking about, Jason? Like, duh, it was 10 billion. Wrong. I'm like, no, you just didn't hear about this one. This one happened before the $10 billion investment. So now the thing is, this was a big deal. This was like, but it wasn't iPhone level yet. Like, my mom didn't know what a GPT was, and my kid didn't know what a GPT was at this moment. But very shortly after, OpenAI, and they get some credit, they also pulled another piece of technology and tacked it on. Now, the interesting thing to note, and it's just an interesting thing that people should understand. OpenAI didn't invent most of this stuff. They're like the folks that invented the nuclear power reactor, which is an engineering feat out of the science of understanding uranium and nuclear fusion and fission. So like, you've got these scientists that are discovering nuclear fusion and fission, and they're like, oh, this is amazing power. This is amazing power. And it could be used for all kinds. I don't know how it'll be used. I mean, you can blow stuff up with it, I guess. Or you can, or maybe you can harness it for power. Who knows? Anyway, there were some folks that went off and pioneered how to blow stuff up. Not awesome. And then there's some folks that pioneered how to harness it for energy. And that's an engineering effort. And so OpenAI really, and this is actually very important work, right? So it's not to diminish that kind of effort, because this was proof points that inspired a generation, the next generation, your generation, and future generations. But they basically took something called PPO, so human feedback reinforcement learning, HRLF, RLHF, sorry, reinforcement learning with human feedback. So they took that technique, which was something that was studied, and PPO, principle, it was a policy proximal optimization, and they essentially applied it to what Google invented, which was this decoder, right? So essentially what that means is this model, the GPT-3, essentially could give you sentence completion and good embeddings, and you could do some prompt engineering type stuff. Let's call it zero-shot, few-shot prompt engineering type stuff, but you couldn't talk to it like it was a human. And so for ChatGPT, they use this RLHF to have one model simply score the goodness of what the other model was doing, right? So it can get smarter. So it's this idea of like a student-teacher type organization of a model, where you have two models fighting each other, automatically getting smarter and smarter, right? And so it's two GPTs, two large GPTs, right? One that just gives you a score as to how good was your output. And then the model that's learning is trying and then getting better at getting better scores, right? You take one GPT that just scores 1 out of 5, 5 out of 5, 2 out of 5, 3 out of 5, 1 out of 5 in terms of how good the response was. And the other model was like, oh, what if I say this? Oh, that's a 1 out of 5. No. All right. What if I say this? Oh, that's a 2 out of 5. Okay, that's better. What if I say this? Oh, that's a 3 out of 5 to the same question, right? That's a simple way to understand how this RLHF works. And so that's what produced a ChatGPT. And that actually is one of the most important notes here, is this is a demonstration of reinforcement learning being applied to invent something that was groundbreaking in practice. There's a lot of research on reinforcement learning. There's a lot of interesting results with models that plays games, but like automatically and so forth. But there's very few big deals of that type of technology being applied for a cross-cutting, world-changing application in practice. And this was one such realization. This point, Microsoft was like, all right, dude, I saw what happened in just a year. OpenAI, we really got to cut a deal. Like, I want all your stuff. I want everything. Give me all of it. And this is the rights to monetize it, right? The rights to be the provider of this stuff, exclusive rights to be the provider of stuff. And they also own half of their subsidiary of their subsidiary of their subsidiary. Is the wildest company organization on the planet. Yeah, and what do I mean? Let me just, I just got to show you, right? OpenAI organizational structure. It's this. Look at this thing. This thing's crazy. It's wild. This is, there's a nonprofit that owns a LLC that controls another for-profit. They have this capped profit company. Who knows what the hell that is? That's what Microsoft owns, a minority investment. It's like 49%. I don't know. And then it's like employees and investors own this other nonprofit thing. Like, what is this? This is their, these are all different companies that is equals OpenAI. It's wild. Anyway, so Microsoft essentially had to make this happen to turn a nonprofit into something it can make buku bucks with, into something that can drive it to be one of those top market cap companies. Because Microsoft, before GPT, was not #1 on the leaderboard, let's say, right? Now they're #1 on the leaderboard because they were able to get OpenAI to do that crazy cockamamie deal. Okay, now, it's important to talk about a very important thing. There used to be a thesis that was across the board. It actually was back in these days. The thesis was models are going to be foundational models. There's going to be very few big companies and maybe governments that are going to train these big behemoth models that everyone's going to like connect to as a service, kind of like AWS, Amazon's thing, connect to as a service and use it for like as a connected service API. The AI will fuel all these products, right? That was the thesis. Like the world was organized in that way, and OpenAI had that thesis too, right? Like everyone's gonna get my GPT's Chat GPT, and that's how the world will be organized. That's been rapidly changing, right? I'm gonna present some really interesting new information today. So they spent $10 billion. I don't even know if it's a good idea anymore, right? Because of what's been happening organically in the community. Remember, it's only been 18 months since this thing started to kick off, right? And in that time, there's a lot of open source models, and there's a lot of smaller models. We're talking models that are 4 gigabytes, 3 gigabytes, 2 gigabytes are being released that can do things that GPT-4 can do. right? That's wild. So this graph is kind of a complex graph to look at, but there's ChatGPT here. So that's ChatGPT. This is all this stuff. But then if you look on the right of it, there's all these open source models. Anything shaded in is an open source model. And this is actually already old, but it does, does this even have Llama 2? Where's Llama 2? Maybe this was pre-Llama 2. I wonder if there's an updated one. I don't know. I don't see it. It might be here. Anyway, Llama 2 is a great game changer. Apparently, there's going to be a Llama 3. There's open source models that are competitive with GPT-4, right? Left and right. And this is actually what the market wants. The market is thirsty for, I want my local LLM. I want an LLM that I can put on my laptop that's as awesome as GPT-4. That's what I want. And whenever you have all of humanity, that's a little bit of a, okay, all of the tech people, scientists, hobbyists, industry folks, they're all working on generative AI. And when the market all wants this thing, don't be surprised if that thing happens. Indeed, that's probably why we have AI, right? So, yeah, so this is a market need, and then the market's reacting. And so we did an analysis in Jaseci Labs, in the incubation lab with Sri Lanka, through the connection between University of Michigan, University of Moratuwa, and all of us together. I mean, we've got authors from Moratuwa, from Sri Lanka, from University of Michigan, like, and in this paper, and it's accepted, and it's essentially, there's a presentation on it at the conference. We'll be presenting it on May 5th at ISPAS, right? The International Symposium on Performance Analysis and of Software Systems, or something like that, right? So in this paper, we did an analysis of these tiny, tiny models. And indeed, I forgot to put, let me just show you how tiny they are. Oh no, I have this. So does size matter? So we're talking about model, like GPT-4 is like the blue whale, right? Which is the largest whale on the planet. It's like huge. It's 200 times larger than a housefly, right? That's the size differential we're talking about. Can models as small as a housefly compared to a blue whale be competitive with these GPTs? And what we found in this paper is, yeah. So we did this Coke test. We did a Coke versus Pepsi. You know, the Pepsi battle, where it's like you put a blindfold on, you taste it. Is it Coke? Is it Pepsi? Can you tell the difference? We did an experiment like that. It's represented by this graph on the right. GPT-4 is the first graph, and folks are scoring the quality of the responses. So this isn't a real product. It's in one of the products that's built using open source Jaseci ecosystem tooling and so forth. So people were ranking GPT-4 responses across a wide range in a real product, in a real experience. And then in that same product, there were small language models like Llama 2 7B. Check out the paper for more details. You can find it on arXiv. And I'll share a link after this talk. But these were the scores across the board with, at the time, many contender models. And each of these models are either 4 gigabytes or less. Some of these models are 1 point something gigabytes. To put that in perspective, by the way, this blue whale is conservative. This is assuming that you have 175 billion parameters. The GPT folks are talking about upwards of 1 trillion parameters, which means it's way bigger, 10x. Actually, 10 of these whales is really the kind of model sizes that folks are talking about these days. But this is a conservative estimate of 175 billion parameters, right? GPT-3, essentially. Anyway, people can't tell the difference in a statistically significant way. Some models do better than GPT-4. I actually have a really great example. It's in the paper of, I'm showing like the responses from 2 tiny models versus GPT-4's response for a real product, AI. And Stable LM is so much better. Stable LM is on here. It's like a 2 or 3 gigabyte model. It's way better than GPT-4. You check the paper to find out more. Anyway, so we discovered that. Of course, it's faster because they're smaller. So basically the highest bars here are GPT-4. And then every other bar is some other model that's tiny and performs really well. So the 3 billion parameter model is like 10x faster or something, you know, like 8x faster when it comes to how quickly you get those tokens, right? Now what? Oh, there's another graph. It's also 25 times cheaper. It's all in the paper. I strongly recommend you check it out. But now what? I think the key learnable from this, right? The key observation here is the market is going democratized, right? They're taking these models, they're making them small, they're fine-tuning them at specific tasks. You don't necessarily need, if you want to solve something, if you want to model us really good at, let's say, just your code base, it doesn't have to be really good at all the other languages. Let's say you just want a Python model that only knows how to work with a certain kind of code base. You can get that model to be really small, fine-tune it, specialize it, and it will crush GPT-4. And there's no need for that model to have the capacity to also know how to solve the bar exam, or how to do an SAT test, or how to do math, or how to do all these other things. You could specialize these models and take ownership of these models. You can make them private, you can make them local, you can make them yours. That's what the human wants to do. And that's what the market wants to do. And so I think we're going in that direction. I don't know what the future looks like for this foundational model thesis. I don't know what the business model looks like if people are going small and companies are open sourcing models, right? So maybe these models will fundamentally all be open source. And then the ingenuity of what you do with the models is what becomes the IP, right? Not the models themselves as trained, right? So just to talk about what's next, like what people are going to be working on, the areas that matter, right? So just like the perfect storm, where innovation always is a tension between multiple factors. And the bottlenecks move, right? So this is a typical computing stack. Models are in the algorithm layer, right? Those are your models. Models, algorithm application layer, that's where your models are. And it's only possible those models can be created today because we had GPUs, we had the compute, we could make them big, we had enough data, we could use the internet to train them, etc. But now we have really interesting models, but no one knows how to build with it, right? And it's way too expensive. Like if you listen to the OpenAI CEO talk about the biggest challenge, he says compute. If you wanted to hire, what was the stat? I'm going to butcher the stat, but it's out there. Go find it on Google or with ChatGPT. But like, if you wanted to like buy 8,000 GPUs, it would take like 5 years if you had infinity money, something like that. Like if you had $1 trillion to get 8,000 GPUs or $100 trillion infinity money, it's not up to you. We got a supply chain. We can't build GPUs fast enough is the point. And the thing is, to train a ChatGPT, to train a big 200 whale model, you need a ton of GPUs if you want to train from scratch. So compute is a bottleneck. How we can build things with it is a bottleneck. And so we've got a great journey in the algorithm and application space. But now we've had stagnation here. We're behind here. We don't really know how to build with these models. We don't really know how to scale these models. We don't know how compute should look like for these models, et cetera, for the future of these models. So everything always moves forward because there's always people working all over the stack, but the bottlenecks change. If you want to understand what the most important, impactful work you can do, it's to work on the bottleneck, right? And we're seeing this in the market. If you look at where the investment money is going, the billions of dollars are going to infrastructure. They're not going to the applications. If you look at industry-specific generative applications on this graph, the investments are 300 million, right? If you look at generative AI infrastructure, it's 11.3 billion. That's the hard part. That's the innovation need. And this is 2023 Q2, from Q3 2022 to Q2 2023. And LangChain, just like 2 months ago, raised $25 million. What's LangChain? It's just a tool. It's an open source tool for trying to make use of these generative AI models now that we have them, right? It's like, how do we build stuff? And there's actually a long list of interesting, innovative technologies that's trying to understand how do we build interesting things with these generative AI models as we move forward. That's something Jaseci Labs cares about, right? So, and we're working on that feasibly. We have an ecosystem of technologies. We have various technologies that help solve this problem. And so I wanted to just take a moment to share with you guys the Jaseci Labs ethos. Our goal is to create and invent the technologies that advance how we code, innovate, and live in the era of generative AI. Everything we do is open source. We are oriented towards sharing. We are writing papers. We're writing blog articles. We want to create the knowledge and share it with the world. We want to create the technologies and share it with the world. Like that's what we do at Jaseci Labs. And we just scrounge for funding. Like we don't like, it's like, I mean, it's always a challenge, but we scrounge for funding just to keep going, just to keep doing amazing things. And we're doing a lot of that work with the incubation lab in Sri Lanka, which is super exciting, a phenomenal lab. So, absolutely engage. I have the honor of leading that lab with Logi, which has been, dude, it's like we're having the fun of our lives working with so many bright people. Anyway, so we have this open source ecosystem of tools that makes this fast. We've built some really cool stuff on these tools. These are real products that are built using our open source ecosystem. So Myca.ai is a productivity tool with AI. It's getting hundreds of users a month are coming on to this tool and using it. There's something that's launching in 2 weeks. It's called Tobu. This is an AI for your pictures. So we worked with a company, Tobu Life, to use our ecosystem of open source tools to build an AI experience. There's also a patent that they did with it, where you can talk about your photos and enrich the photos with your memory. So there's an AI in your phone that knows all of the context around your photos, and then you can relive your memories with all the details you couldn't remember as to where the photo was, like what happened in the photo, how you felt about it, all that stuff. We also built, using this ecosystem of open source tools, Pocket Nest. We just delivered this. This is going to be in production very soon too. This is a company that does a financial wellness app. And there's this awesome AI that will just be your buddy and tell you about your finances and what you can do to do better. And so this has been built. All these things have been built in just 3 months with a small team, which would actually normally, without the Jaseci contributions, the things we're trying to invent, take months. Take years potentially, right? And then there's Zero Shot Bot. So there's all kinds of cool stuff there. We're definitely welcoming anyone that wants to contribute to join the effort, contribute to open source, contribute to documentation, contribute to wherever you're inspired to. And thank you very much. And that's it. So you can reach out to me, just email me or text me or something. There's contact information here. But with that, I'm happy to take any questions you guys might have.
Yeah, so thanks a lot, Professor Mas, for taking us through a like wonderful journey that you have been experienced for a while. So yeah, I think we have lots of raising hands coming in. So I would like to let the audience to ask questions from you. Yeah, first up, I think Professor Maheshi, who was a former chairman of IEEE Sri Lanka section as well. So Professor Maheshi, would you like to go ahead?
Yeah, thanks, Kavinda, Upul, and thanks, Professor Jason, for that lovely presentation. I really enjoyed it. Awesome. I have a small, because it's eye-opening about the industrial application, and I do work on, I try to work on generative AI in research point of view. So with that, my question is, what I even understood with your presentation is all these companies which are working on generative AI, they are like multi-million-dollar companies, and they have access to processing power. So first question is, what's the chance of like a university, especially a local university, working on this generative AI models point of view? Can they work on new models? Will it be like the resources, especially, will it be challenging? But towards the end, you said there are small models. So that's one question. The other question is, like, where do you think the modern development is going? Is it like reusing the existing model and coming up with your maybe a different application? Or is it like designing new models, or like thinking the model architecture from a different fundamental point of view, something like that, or reusing?
Yeah. Oh, that's a phenomenal question. Those are phenomenal two questions. So first question, right? Like, well, how are we going to do research on this stuff? Like, if it's super expensive. So there's, I mean, the short answer, and then I'll describe a little bit more. The short answer is there's going to be a certain set of investigations, inquiries we would want to make that we may not be able to from a cost perspective in academia, right? So, like, if you really wanted to say, okay, you know, the 1 trillion parameter model that OpenAI just did is good. I want to do a test with an 800 billion parameter model. That would still be too expensive for us, right? Or if we wanted to go bigger, we won't be able to pre-train or even run, at least the way funding works, even in the US. Like, we wouldn't have the funding to actually do that research. So, but there is a whole set of questions that we will get to answer, like when it comes to, especially the smaller models, you know, how do you fine tune it? You know, I think that when it comes to pre-training a model is still expensive. It's almost prohibitively, a real competitive model, pre-training one is prohibitively expensive. Fine tuning or techniques related to kind of honing a model to solve specific problems, we can do that work. You know, when you look at, say, the mixture of experts, a technique, this is a technique where you can have multiple models. It's kind of a way to ensemble multiple small models. So Mistral has a very popular 8xB or something mixture. So like, we can investigate techniques to make smaller models better or make models even smaller. So like, questions like that are the most efficient way to fine tune a model. And so fine tuning, guys, to anyone that doesn't know the difference between pre-training and fine tuning is pre-training is how you get the model to learn about the world. So you give it 1 trillion tokens to read. And then after that, you can actually hone its intelligence. Indeed, ChatGPT is actually a fine tuning technique where they took that pre-trained model and they just fine-tuned it to be a good conversationalist, to be able to talk about what it understands about the world. And so fine-tuning is around that. We can do a lot of interesting work, prompt engineering, and people are starting to call it different. The names just change so rapidly. It's zero shot, few shot, now it's prompt engineering. Someone called it prompt-based learning. And I'm like, dude, I don't think you get to say learning because the weights aren't changing. Anyway, so that's the first question. The second question was, oh, what was the second question?
Like modern research, is it more towards designing new models or using the existing models in applications?
Exactly. So I actually think that there's a lot of greenfield problems to solve outside of the designing new models technique. Now, there are some folks who are just model people. Like Yann LeCun has a whole thesis as to what the next transformer should be and how we should go into an embeddings. He wants to take it out of this model just writing word after word down to a models that reason in the embedded space. So like, there's some folks working on that. Let them work on that. But I think that there's so many challenges around the wielding of these models, right? So it's like, how to efficiently fine tune them. What's the cost of like shrinking? These are the things I care about a lot. So I'm using them as examples a lot. But you know, like, how do you program? Like, one of the things we're spending a lot of time on is, what does it mean to code in this new era? And can models replace function bodies. What if I have a function like personality? I want to get the personality and the parameter is a name. If I go to ChatGPT and I ask what's the personality of Einstein, that's the kind of problem that only a model can solve. Like you can't have if-else statements that'll solve that when you get the name, but only a model can solve that. So can we code with a new kind of function as a concept? And so like how we code with in this new era, like the tooling around it, how do we build with these models if they're small, if you want multiple, or if you want one general one? I think there's a lot of work to do there. That's where I'm focusing. You know, good questions.
Thanks. Very, very detailed answer. And
yeah,
thanks a lot. Thanks for sharing.
Yeah, no worries, no worries. Cool. Any other questions?
Yeah, it's open to the audience. You can either like unmute yourself and ask.
Right. I see one in the I see one in the chat actually. So there's
okay.
How are smaller models made? Are they made from larger models? Yes, they are. So yeah, so I'll try to be a little bit more precise with the answer because I do love to talk about this stuff. But yes, they are. Here's the interesting thing. Facebook has been releasing their pre-trained models, right? So they'll release these big pre-trained models like Llama 2. They plan to open source Llama 3. What's really been happening is with these small models and these other challenger models is they take these larger pre-trained models and they'll build models out of them. So there's usually a couple different sizes that are pre-trained organically. And then often the ones that we experimented in that paper were the small ones, the 7 billion parameter ones. And we essentially took the quantized version. So there's a way that you can make the weights tinier by using less bits to represent them. So quantization and taking the smaller versions of the bigger models is really the art that folks are using to get these models to be small. However, there are techniques to fine tune the small model. So if you have a good, you know, pre-trained tiny model, you can just get them to be really, really good at what you need them to be with good fine-tuning techniques. So, and you know, you don't need to keep updating the pre-trained model by and large, right? Like the concepts of the world and what a king and queen is doesn't change that rapidly. So you can just fine-tune any kind of new information you want it to have, or fine-tune any kind of new capabilities it has. And so I can see a world where, okay, like I don't need to update the pre-training. I'll just use this fine tuning for like a decade, you know what I mean? And then I'll just wait for someone to open source some big model, or it'll get cheaper. So yeah, good question. Is it true that AI is going to replace programmers in the future? Depends on what you mean replace. Here's the thing about human psychology. No one ever will rely on a model to be accountable. That is, if I work for Microsoft and I'm a programmer, I'm the only programmer that builds their email client, replacing me with a model, when there's a bug in that email client, they're not going to want to go to the model to be like, oh man, there's a bug, you need to fix it right away. They're not going to do, they're going to want humans to be accountable for, they're always going to want a human to be accountable for whatever work. So I don't think it'll replace humans as a completely, or programmers completely, but what it'll do is it'll take one programmer and allow them to be as productive as 5 programmers today. Let's say in 2 years. So that means your team of 6 programmers could go down to 1. You know, so there will be jobs lost. The market is going to change in terms of supply demand dynamic between different roles in the company. Certainly, it's going to be very disruptive in that way. But yeah, so but I think one of the biggest mistakes happening right now is I feel like this narrative is discouraging many people from pursuing programming and engineering and stuff like that, which is a massive myth and mistake. What'll happen is the nature of productivity, just historically, is when we get more productive, the expectations of how productive we are increases and we move faster. So let me give you an example. If a company has a technology that makes their engineer 5 times more productive, the company can stay with the same level of productivity and reduce their team, or the company can be 5 times more productive. So Apple can create 5 times more products. People can buy 5 times more products, right? Like, it's like the whole world just moves faster, right? And so you're going to need those 5 engineers, but those 5 engineers are going to have to learn the skill of wielding models. You know what I mean? That's actually what's going to happen. So it's not like there will be less jobs. I mean, some companies might do that in short term, but then companies are going to still want to move as fast as they can, right? They're just going to do more innovation more rapidly. They'll build more software because of AI. So yeah, that's how I think about it. Stay in the game and just learn how to use the AI to help you be productive. What is prompt engineering? Oh, go ahead. Is there an in-person question?
No, you can go ahead with the
yeah. So what is prompt engineering, and is it going to be an actual in the future? What is prompt engineering? So prompt engineering just means controlling what the model will say just by talking to it. You can think of it as that. It's like if you want the model to do something, say with your personal bank information, you can actually either have the model updates its neurons with your bank information, or you can just tell the model with the same neurons your bank information, and then say, okay, this is my bank information. Now tell me what you think I should do based on. So prompt engineering just means using words to control the model's behavior instead of training the model, updating its weights to control its behavior. It's kind of 2 vectors of control. If you're teaching to computer science students, what should you focus in terms of courses, technical content, other than soft skills and skills that students need to know? See, it is a big misconception that a lot of students want to go work in AI. What's really happening, guys, everybody, is the whole stack is being optimated with the objective function of AI. So it's almost like saying, when we invented the internet, a lot of students might be like, oh, I just want to take internet courses. I just want to take networking internet courses. I don't want to learn about processors or systems or programming languages or AI. I just want to do internet courses. Big mistake, right? Because all of these technologies need to move forward in tandem to realize AI. So let me rephrase. Almost every discipline is AI today. So in programming languages, the programming languages are evolving to better support AI. In processor, in the computer architecture, the computer architectures are being designed to be able to make AI training and inference faster. So you could be a computer architect, you could be an electrical engineer, you could be a programming language person, you could be an operating systems person. Everyone is working on AI, even across disciplines. I actually would say, there is more scarcity because everyone's working on AI. There are other areas that have a lot of scarcity. For instance, compilers. Every one of these companies, Microsoft, I know this. I know the people who do, these are my buddies, right? Google has like 1,000 people that just work on compiling neural networks. It's neural networks have to be compiled to the hardware, right? You go from neural network transformer to processor. That's a compilation task. PyTorch, TensorFlow, they're compilers. PyTorch is a compiler, guys. And guess what? No one's studying compilers because it doesn't sound like AI. So there's a shortage of folks who know how to do compilers. And the market is, so they get jobs quickly. So I would say work on something that you're passionate about. Don't worry if it's called AI or not, because it's all AI. You know what I mean? So that's how I would answer that. As a beginner to the industry, what should I when should I start? What are the sources that can be really helpful to me? Oh, one of the beautiful things is that we live in an age where information is abundant and easy to access. Depending on where you are and what you want to do, I would be strategic in finding the best resources and projects to build. One thing that I think a lot of folks miss out on, it's not watching videos or even reading books. It's building things. In engineering, like the best way to learn is building things. So just pick a project, then find the relevant tutorials for that project and build it. That's the best way to learn anything. So I think you start with identifying that project and then let the project guide you to what to read, what to learn in order to build it. Cool.
Right. Yeah, so Professor, like, let me also like get one question for you. So I mean, you might have covered this in different ways, but so in my perspective, generative AI model is, in my belief, so far, is more of a better personal assistant. I would rather say like the best personal assistant that we could have, rather than a self-driving entity itself. Because to like the major issue that I have seen in the generative AI is the hallucination, and it needs good prompts or good prompt engineering to be inserted by a human to get it to work well. So I see prompt engineering itself, like prompt engineering seems to be important as model itself. So do you agree with this, or otherwise can you elaborate?
No, I actually, I tend to agree to a surprising degree. So, and this is a very good nuanced point. In the near term, like very few people are actually training and fine-tuning models to their problems in today's world. I'm not aware, even in commercial deployments, whenever people are wheeling these models, they're essentially prompt engineering first. There's many reasons why an argument could be made that you should never fine-tune for a problem that could be solved with prompt engineering. And the number of problems that require fine-tuning today are very small, right? Given the technologies we have. So LangChain is essentially a prompt engineering toolkit. And there's many. There's one that's rising called DSPY. There's another one called SGLang that we were looking at. There's a Llama Index, which is essentially starting to build everything that LangChain has. And this is essentially how people are building products today, is with leveraging these tools, agent-based approaches, memory-based approaches. There's new abstractions and concepts being kind of emerging in the prompt engineering realm. So I think it's an absolute reasonable. That's a very good point, and it's a good point to share and help people understand. Indeed, I think the research there is going to have the most rapid uptake by the industry. So I agree.
Thank you.
Yeah.
So on the other hand, like I was so encourage you because of the what you said is like the more investments nowadays are into the infrastructure even than the applications themselves. So because I'm coming from a background of a computer architecture, processor design, rather than on data science itself, even though I have some background on that one. So in your ideas, what would be the most attractive infrastructure in the future? Like, would that be like more investment on the GPUs themselves, or more customer specific ASIC processors to run on the run the AI?
That's a really good question. So I love that question. Hold on real quick. I'm just trying to get. Oh yeah. So no. So I have this gesture-based system. Yeah, don't worry. No, I love that question. So that's right on. Actually, so first I'm going to start by saying I I've done computer architecture work. I've done operating systems work. I've done compilers work. I've done programming languages work. I've done AI work. So honestly, I really do believe that when you're working on problems, you should integrate all of the perspective you have to work on that problem. And so I applaud you because I'm like you in this way, right? Like you just work on interesting stuff no matter where it is in the stack, and you hack that problem. Now, for me, I think that the most important area in I think the most important problem area is one where we build architectures that will allow us to host our own models on our laptops. I think that would be one of the North Star visions that you can then ideate like what is the right architecture for. People are going to want in their tablets and laptops to be able to have the AI there in their phones. And okay, let's assume that. So then let's work backwards. So if you look at what NVIDIA is doing, they're actually bringing compute in as an integrated, they're integrating their own custom-built, vertically integrated CPUs now with their GPU architecture. So they just launched this thing where they're, and we know that that vertical integration, and when you control the memory interface between CPU and GPU, if you can control the design of that, and you control the design of the CPU itself, and then the GPU itself, you control the whole vertically integrated stack, you can build the right thing to get the highest throughput, the highest efficiency. So I think we're going to see more vertical integration. Apple did this in laptops. Apple is crushing it right now with their CPUs, now that they can control the entire memory stack from applications all the way through. So I think we're going to see much more co-design from companies, at least from the industry's perspective, but co-design as a thesis, as a theme in your work, I think is going to be even more important now than ever, because that's what the market's doing, is co-designing things. And so what can you co-design inside of a laptop? Do you have how do you then, like, what should the future SIMD architecture look like on a CPU? Do you just make the vector unit on the CPU look like a GPU more, or be tuned for inference? Is there some kind of specialized GPT accelerator that you would want to have integrated into the CPU? Basically, any of those ideas you could write a paper on today, because this problem space is so new. So I think that from an architecture standpoint, that would be the work I did, coming from a thesis. Everybody wants democratized model to run on all hardware. You should be able to train and infer with local generative AI. What does the machine for that look like? I think there's a lot of opportunity there.
Right, cool. So one quick question to end my my set of questions. So now, since like specifically the large language models, and even if you take a small language model, takes quite a considerable amount of power to, like, even not just for the training, but even for the inferencing, it takes a massive amount of power. So when it comes to like things like IoT systems and all, like edge devices, we need to consume a lot of power. We need to conserve a lot of power. So nowadays, like, what is the major trend? Are they mainly working on low power designs, or high performance designs, or a hybrid of these?
Yeah, no. Well, so I mean, IoT actually has a spectrum of constrained environments, a spectrum of constraints. People are trying to put more compute near the sensor, right? Like, so there is a trend where there's a lot of investigation as to what can you do at the stage of the sensor to make more efficient the work that might need to go to a base station, right? So architectures are getting more interesting. When it comes to something at the scale of a transformer neural net, I haven't seen a lot of work where folks are trying to solve problems at that scale. I'm really thinking about the real, like, constrained environments where you've got very little power and energy to work with. I haven't seen anyone put sophisticated hardware where you'd run, say, inference on a transformer in the in the device. And I actually don't know if that would be I don't think it's a good idea today. You'd have to almost assume it's a connected device, but you know, of course, if it's connected to a phone, then you can run the transformer network on the phone. So I'm seeing more advanced pre-processing that's happening at the level of the sensor to optimize the data that needs to be sent out to a connected device as kind of a trend there. But you know, I mean, I don't know, like things are moving very fast, and you know, I wouldn't be surprised if people are getting beefier on all over the place, right? Or more ASIC acceleration. Someone might come out with an ASIC that you can run a tiny 1 gig model on an edge device. That's open for research, man. Like that's an interesting idea.
Right. Thanks, Professor. Thanks.
Yeah.
So I think like, we have, I think overshoot the time quite a bit.
Yeah, I
because
know.
of the interesting, like the level of interest that people have
Yeah.
in the, like, lot of questions coming in, like flowing in. So that itself shows the interest of the people
Yeah.
we had. So I mean, it has been amazing that we had like more than like nearly 100 participants in an online webinar. So that itself shows
That's awesome.
the enthusiasm.
Yeah.
This is super nice.
Yeah.
So before concluding, ladies and gentlemen, I would like to take a moment to extend our heartfelt gratitude to our esteemed speaker, Professor Jason Mas. I mean, he might not be a new face for some of the folks, even in Sri Lanka. He has been working with several people connected to the University of Moratuwa. So, so your insights into the emergence and future of generative AI have been truly enlightening for the audience. Your passion for the subject and your dedication to the advance in the field are evident in every word you have shared with us today. Thank you very much, Professor.
Yeah.
So
Thanks for having me. It's been a pleasure. Yeah. Thank you.
Yeah. So then basically, like on behalf of IEEE Industrial Electronic Society and IEEE Sri Lanka section, I would like to express my heartfelt gratitude to you, and as well as our amazing audience. I must say, like, big thanks goes to our amazing audience that who present today, and it was very interactive as well. And then finally, once again, I would like to thank Dr. Logi and Dr. Ruantika both towards the support you have given to get this session done in time. So thank you very much, everyone. So with that, I would like to conclude today's session and hope to get back to get back to you another session, maybe a physical session once you're back in Sri Lanka, Professor. So hopefully to connect with you once again in the future. Thank you so much.
Yeah, absolutely. This summer. So yeah, we'll make sure everyone knows. I would love to do an in-person in the summer when I'm there. So yeah,
absolutely.
keep me posted. Yeah,
sure. Thank you very much then.
Awesome.
So have a good day to you, and have a good night to everyone in this region. Thank you very much, and hope to see you once again in a productive webinar.
Yeah, thank you so much, guys. Yep. Yeah, stay in touch. Yep. Bye.
Thank you.